Okay, let's continue. So let's again use the very basic dice rolling to be our first example. Okay, suppose X is the outcome of rolling a fair dice. In that case, you know what's the population. Okay, this is the population. Why do we say it's a population? You may imagine that, okay, when you have a dice, you can roll it again, and again. If you roll the dice infinitely many times and collect all the outcomes, that would be your population. Okay? And if you cannot do that, if you roll the dice just for 1 times, 5 times, 1,000 times, that's some sample. Okay, so when you have your population capital X, in that case, you know what's the probability distribution, right? The probability distribution is that the possibilities are X may be from 1 to 6, and the probability for each value is exactly 1 over 6. They are all the same. In that case, we may calculate these parameters. These are some important values for our population, right? Mu, the population mean, is calculated in this way. Each value weighted by its probability to happen. And if you want to do the calculation, you may list all the possible values, all their probabilities, and this value would just be 1 times 1 over 6 plus 2 times 1 over 6, blah 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 blah, up to 6 times 1 over 6, and that's going to give you 3.5. Then you may calculate the population variance. It's that for each value, you find the difference from it to the population mean. Take a square and then weight all these squares by their probabilities, like this. For x equals 1, the difference between 1 and mu is 2.5, and then the square is 6.25. For 2, the same thing, but the square is just 2.25. So you have all these 6 numbers, you weight all these 6 numbers by their probabilities, and then you get sigma square around 2.91, 2.92. And then the population standard deviation is just the square root of your population variance, so it's around 1.7. So these are some basic calculations that we already know how to do in about 2 weeks ago. Okay, well, nothing special. So we can describe our population if we have our population distribution. Now, we'd like to do some sampling and say something about our sampling distribution. So let's say that we roll the dice twice and get 2 values. Of course, we would say that they are independent, right? Because if today you get 1, it has nothing to do with whether you will get 2 tomorrow. So let x bar 2 be our sample mean of this outcome. Okay, so x bar 2 again is a random variable. Our theorem tells us the following. For this random variable x bar 2, its expected value would be the population expected value. So it would be 3.5. Okay, they would be exactly the same. And then for our random variable x bar 2, the standard deviation can be calculated by this formula. Okay, the numerator is the population standard deviation, the denominator is square root of 2, and then we get around 1.2. So what are the implications here? First, the expectation of our random variable x bar 2 is the same as the expectation of the population. So we expect x bar to be around 3.5, just like our population x. Okay, the expected value of each outcome is 3.5. So you can see that if we look at the formula again, when we want to calculate the expected value of x bar 2, it obviously depends on the expected value of x1 and the expected value of x2. Today you roll 2 dice. the first outcome is expected to be 3.5. Okay, the second outcome is also expected to be 3.5. And that's your expectation of each outcome. So you get an average of the two outcomes. Again, it's 3.5. So that's nothing special. And then what's more important is that when you calculate the standard deviation of your sample mean, it's something that is smaller than your population standard deviation. Okay, that means the variability of X bar 2 is smaller than the variability of capital X. When you roll one dice, you have some variability. When you roll two dice and find their average, according to your intuition, you know the values would be typically around 3.5. And if you want to have a very large sample mean, basically you need both values to be large, right? Just like the example or the comparison here. Let's consider the probability for X or for X bar 2 to be greater than or equal to 5. For capital X, you have two possibilities. You have 5 or 6 that are considered greater than or equal to 5, right? So 2 out of 6, the probability is 1 over 3. For X bar 2, it's harder, because if you want X bar 2 to be greater than or equal to 5, your X1 and X2 must be, for example, 4 and 6, 5 and 5, and 6 and 4. So you only have 3 possibilities out of 36 total possibilities. So that means you only have 1 over 12 as your probability for X bar to be greater than or equal to 5. So this confirms your intuition. If you want your sample mean to be large, you need both values to be large in this example. Okay, and obviously that's hard. In many cases, it would be one value is large and the other value is small, or the other way. So the large and small values would offset each other, and the sample mean would be around the population mean. If you want an extremely large or extremely small value of X bar, you need both values to be large or small at the same time. And of course, that's rare. Okay? And when extreme values would occur in a small probability, you know it's easier for you to predict the outcome of this random variable, right? Only rarely we have extreme values. So most cases we would have common values. That means something around the population mean. Okay, so that's our first example. If we do one thing further, we may try to ask, what will happen if we roll the dice 4 times? In that case, we denote the sample mean as X bar 4, which is again the arithmetic average of X1 to X4. The theorem would tell us that mu X bar 4 is again 3.5, but sigma X bar 4 now it becomes even more smaller. Now it's become around 0.85. In general, obviously, we know it's not something that we see by chance. It must be that, because sigma X bar 4, the formula is sigma over square root of 4. And sigma X bar 2 is the square root, is sigma over square root of 2. So that's why this is smaller than that. And that means the variability of X bar 4 is even smaller than that of X bar 2. So why is that? When we have 4 values together, 4 outcomes of rolling a dice, if you want X bar 4 to be large, then you need most of the 4 values to be large, right? For example, if you want X bar 4 to be 6, then you need all 4 values to be 6. Which is very difficult. If you want X bar 4 to be greater than or equal to 5, you have a few options like 3, 6, 6, 6, 4, 4, 6, 6, and so on and so on. But as long as you get one dice being 1 or 2, then you're dead. Okay? So again, you need most of the values to be at the same direction for you to have a large or small sample mean, and that's rare. That's why it's easier to predict your sample mean when your sample size is larger. That's why when your sample size gets larger, your sample mean would tend to be quite close to your population mean. That means the standard deviation would be small. So in general, when two random samples of size n and m are collected from a same population, then that x bar n and x bar m to be their sample means, then we have, if n is greater than m, then x bar n would have a smaller standard deviation than x bar m. Okay? When you have a larger sample, size, then the sample mean would have smaller variability. The standard deviation of your sample mean would be smaller. So let's consider another example about our candy factory. So the weight of a bag of candies, let's assume for a while that it follows the normal distribution with mean 2 and a standard deviation 0.2. Let's assume this is true. Suppose the quality control officer, or suppose in our factory there is a factory control officer. The quality control guy will sample 4 bags and calculate the sample mean x bar. The decision will be made about whether my process is wrong according to the sample mean. If the sample mean is not within 1.8 and 2.2, the officer will make a report and fire me or something. So that means I hope this sample mean should be within 1.8 and 2.2. Note that this investigation or this quality control process is again random, right? My production process in some sense is good because mu is 2, right? Mu is 2. So mu is really within the ideal interval, 1.8 and 2.2. Unfortunately, it's not perfect. That means it has a positive standard deviation. There is some variability. So we may still be punished if we are unlucky. If, unfortunately, all the 4 bags that are randomly drawn are too heavy or too light, and that's possible. So I would like to know what's the probability for me or for us to be punished, right? That's something we want to know. What's the probability for a lot of candies to be rejected just because we are unlucky? So we want to calculate this probability. For x bar, that's the random sample mean. Okay, if sample mean is within 1.8 and 2.2, then we're safe. Otherwise, we are not. We want to calculate this probability. There is something we know. We know that the mu and the sigma for our sample mean is 2 and 0.1. And 0.1 is calculated from 0.2 in this formula, okay? Because we have 4 bags, so the standard deviation gets to only 1/2. But even though we know the mean and the standard deviation, it's not enough for us to calculate this probability, because we really need to know the probability distribution of x bar. Okay, we need to know it's normal, it's uniform, or it's something else. We need to know the distribution. Only knowing the mean and the standard deviation is not enough. So what may we do? We don't know. So how about let's do an experiment first. So before we tell you some theorems, let's do some experiments. So I would like to simulate to simulate the process of making candies and the process of getting random samples. So first, I would like to generate 4 random numbers following the normal distribution 2 and 0.2. That's the next 4 bags of items and 4 bags of candies that I will produce. Okay, And once I do that, I should follow the population distribution. When I get that 4 values, I can calculate x bar, my sample mean, and I want to repeat this for 5,000 times. The reason to do that is because I then can draw a histogram for that 5,000 random outcomes. Okay? When you have a random variable, and when you have some kind of observed values, okay, like these 5,000 observed values, you can draw a histogram, and that histogram tends to tell you what's the probability distribution of that random variable, right? Something we did in the previous lecture. So here is the result of my experiments. The mean of the 5,000 values is indeed around 2. The standard deviation of the 5,000 values is indeed around 0.1. Okay, so that's good. What's even better is that the distribution here looks like a normal distribution. Of course, if you do this 5,000 today, another 5,000 tomorrow, you will get different values. So you're going to see a somewhat different distribution or histogram. But I promise you, if you keep doing that, always you will see something similar to this. Okay? This is a histogram for that 5,000 random outcomes. And it will always look like a normal distribution. Finally, we can count the number of random outcomes, the number of random outcomes that are above 2.2 and below 1.8, and that's around 4.68%. If you do this repeatedly, you will get different values, but they should be somewhat close to each other. So this gives us a conjecture about, it seems to us that x bar is roughly the normal distribution, okay, and its mean should be 2, and the standard deviation should be 0.1. Okay, so we get this idea, so let's try to confirm it. To confirm it, we know that if this is the truth, if x bar is really a normal distribution with mean 2 and the standard deviation 0.1, each time when we use it to generate something, the probability for that to be greater than 2 should be exactly 1/2. And the probability for x bar to be too extreme would be around 4.5%. Okay? So we know that our experiments is only a sample outcome. So it cannot perfectly fit these numbers, but our outcome should be close to these theoretical outcomes. So let's do multiple rounds of these experiments. If I say, for example, I do 4 rounds, I probably would get these sample means all close to 2, these standard deviations all close to 0.1, and these probabilities, or I should say proportions of values that are greater than 2, well, there are some fluctuations naturally, but they are around 50%. And the number of x bars that are above 2.2 and less than 1.8, again, there are some fluctuations, but they all are around 4.5%. Okay? If you increase the sample size from 5,000 to 10,000, 20,000, and so on, you would see these values even more close to 0.5 and 0.04.5. So that means we tend to believe that x bar is really a normal distribution. Okay, it's really a normal distribution. It turns out that this is true, and we will do some more discussions in the next video. Thank you.